For decades, the moon has been treated as one of the most reliably dead places in the entire solar system. A cratered, silent rock, frozen in time since the last major impacts billions of years ago. That assumption is wrong. Beneath its ancient, motionless-looking surface, the moon is still shrinking, still cooling, still quietly cracking its own crust apart from the inside. And it is doing so most actively in exactly the region NASA is now planning to send astronauts to live and work in for the first time in over 50 years. This isn't speculation. It's the conclusion of a NASA-funded study, backed up by new data released just this year, and it's already changing how engineers are thinking about where it's actually safe to build a permanent human outpost on the moon. Here's the basic physical process driving all of this. Like any large planetary body formed billions of years ago, the moon was once far hotter than it is today, carrying a substantial amount of internal heat left over from its violent formation. Over the eons since, that heat has been steadily, relentlessly radiating away into space. And, as the moon's interior has cooled, it has also slowly contracted. The same basic physical principle that causes almost any material to shrink slightly as it loses heat. According to NASA's own measurements, the moon's diameter has decreased by roughly 50 meters, about 150 feet, over the past several hundred million years. On a body the size of the moon, that's a small, gradual change, but it's not a change without consequences. As the moon's interior shrinks, its outer crust, brittle, rigid, and far less able to simply compress smoothly along with the interior beneath it, gets squeezed. That squeezing eventually becomes more than the crust can absorb quietly, and sections of it break, sliding up and over adjacent sections along what geologists call thrust faults. On Earth, thrust faults form constantly, as part of the ordinary churn of plate tectonics. The moon has no plate tectonics at all, no moving crustal plates sliding against each other the way they do here. Every thrust fault forming on the lunar surface today is happening for one specific, singular reason. The whole moon, as a unified body, continuing to slowly shrink around its own cooling core. These fault lines leave a very specific, very recognizable signature on the surface. Features called lobate scarps, long curving cliffs or ridges where one section of lunar crust has been thrust up and over the ground beside it. Scientists have been documenting these scarps across the moon's surface for years using high-resolution orbital imagery. But the critical, more recent question wasn't simply where these scarps exist, it was whether they were still actively forming today, and whether that ongoing activity was producing genuine seismic events, actual moonquakes, capable of shaking the ground the way an earthquake would here on Earth. The evidence connecting these two things together comes from an unlikely source, the Apollo missions themselves. Between 1969 and 1972, Apollo astronauts deployed a network of seismometers directly onto the lunar surface, instruments specifically designed to detect and record ground motion, exactly the way seismologists monitor earthquake activity here on Earth. That network, called the Apollo Passive Seismic Experiment, continued operating and quietly recording data for years after the astronauts themselves returned home, eventually being switched off in 1977. Buried within that decades-old dataset is the record of one of the strongest shallow moonquakes ever detected, an event with an estimated magnitude around 5 on the Richter scale, powerful enough, if it occurred on Earth, to be unmistakably felt by anyone nearby, even if it would likely only cause fairly minor structural damage given that specific intensity. For years, the exact epicenter of that specific quake couldn't be pinned down with real confidence, because the sparse network of seismometers scattered across the moon's surface simply didn't provide the geometric coverage needed to triangulate a precise location the way modern, densely spaced seismic networks can here on Earth. But researchers led by Thomas Waters, a senior scientist emeritus at the Smithsonian Institution's National Air and Space Museum, went back to that old Apollo data with modern analytical tools, specifically a relocation algorithm designed to work with exactly this kind of sparse, limited seismic network. What they found was genuinely significant. The range of possible locations for that powerful ancient moonquake's epicenter clustered directly around, and overlapped with, a cluster of these young, active-looking lobate thrust fault scarps in the moon's south polar region. The exact same broad area NASA has identified as the leading candidate zone for the Artemis 3rd mission, humanity's planned return to the lunar surface with astronauts for the first time since the Apollo program ended. That overlap is exactly why this research matters so much right now, well beyond simple scientific curiosity. Waters and his colleagues didn't stop at documenting the connection between the old quake and the nearby faults. They went further, specifically modeling one particular young thrust fault scarp located within an area called Daguerreotype Rim 2, one of NASA's actual candidate landing regions for Artemis III, to understand whether a moonquake of that same historically recorded magnitude could plausibly happen again there, and if so, what that would actually mean on the ground. Their modeling suggested that shallow moonquakes capable of producing genuinely strong ground shaking in that south polar region remain entirely possible today, either from renewed slip along faults that already exist, or from the formation of brand new thrust faults as the moon's slow, ongoing contraction continues. And the consequences of that shaking aren't limited to simply feeling the ground move. The researchers specifically modeled how the loose, fine, powdery lunar soil, called regolith, covering much of the moon's surface, would respond to that kind of seismic shaking on sloped terrain, and the results were genuinely concerning for anyone planning to build permanent structures there. Steep interior slopes within certain craters, including the deep, permanently shadowed walls of Shackleton Crater, one of the specific sites under consideration for Artemis III, given its potential to harbor water ice in regions that never see direct sunlight, were found to be particularly susceptible to landslides, even from comparatively modest seismic shaking. That's a genuinely serious engineering consideration for any mission planning to send astronauts down into, or build infrastructure near, exactly that kind of terrain. NASA published these findings, along with a formal paper, in the Planetary Science Journal, making the underlying message explicit and direct. The global distribution of these young thrust faults, their apparent potential to remain seismically active, and the ongoing possibility of entirely new faults forming as the moon's contraction continues, all need to be factored directly into how future permanent lunar outposts are actually sited and engineered, not treated as some distant theoretical afterthought. Renee Weber, a co-author on the research based at NASA's Marshall Space Flight Center, was candid about how much is still genuinely unknown here. To properly understand the actual seismic hazard facing future human activity on the moon, she explained, scientists need considerably more new seismic data, and not just concentrated around the South Pole specifically, but gathered globally across the entire lunar surface. Missions currently being planned, including one called the Farside Seismic Suite, are specifically intended to expand on the original decades-old Apollo measurements and build a far more complete picture of exactly how seismically active the moon actually is today, across its entire surface, rather than relying primarily on a handful of aging instruments from missions that ended nearly 50 years ago. And the story hasn't stopped developing even since that original 2024 study was published. Earlier this year, in 2026, researchers went back through the Apollo-era data again, this time incorporating an additional, previously underused instrument into the analysis, the Apollo 17 Surface Gravimeter, a device originally intended to measure subtle variations in the moon's gravitational field, repurposed here to function as an additional seismic sensor, helping refine and improve the calculated locations of several previously identified shallow moonquakes. That refined analysis produced a genuinely intriguing new wrinkle in the story. At least one of these shallow moonquakes turned out to overlap with a major crustal gravity anomaly, a subtle but measurable irregularity in the moon's gravitational field, associated with what scientists believe is a large ancient volcanic dike buried beneath the surface, a solidified channel of magma that once fed volcanic activity deep within the lunar crust long ago. That overlap raises a genuinely open scientific question. Was that particular moonquake actually caused by the same kind of shallow, cooling-driven thrust faulting responsible for the others? Or does it instead point towards some deeper, more complex seismic source connected to ancient volcanic structures still buried beneath the surface? Structures that may still, in some subtle way, be influencing the moon's geological behavior even today. As the researchers behind this newest analysis put it plainly, lunar seismicity isn't a single, simple phenomenon with one clean, unified explanation. It's a genuinely complicated picture, made up of at least a few different kinds of moonquakes, driven by a few different underlying physical processes, some clearly tied to the moon's ongoing gradual cooling and shrinking, and others potentially connected to older, deeper structural features, whose full influence on the moon's current behavior isn't yet fully understood. None of this means the moon has suddenly, dramatically come alive in any explosive, catastrophic sense. It hasn't developed active volcanoes, and there's no indication of any sudden, unprecedented surge in seismic activity happening right now. What these findings actually reveal is something quieter and, in its own way, more genuinely important for the specific moment humanity currently finds itself in. A world that was, for decades, simply assumed to be geologically finished, entirely locked in place, still turns out to be slowly, steadily active beneath its ancient surface, cooling, contracting, and periodically shaking, exactly in the specific region where astronauts are now scheduled to actually try living and working for extended periods for the very first time. That's why this particular piece of science carries weight well beyond academic interest. It's not an abstract curiosity buried in a research journal. It's a direct, practical input into decisions currently being made about where, specifically, to place permanent human infrastructure on another world, decisions where getting the underlying geology wrong doesn't simply mean an inconvenient research correction later. It means genuine risk to future astronauts, spacecraft, and the multi-billion-dollar habitats currently being designed to support them. The moon spent billions of years convincing us it was finished changing. It wasn't lying, exactly. It was just changing on a timescale so slow, so quiet, that it took precision instruments left behind by astronauts half a century ago, and a fresh round of careful, modern reanalysis of their forgotten, decades-old data to finally reveal that the ground future explorers are planning to stand on is still, however subtly, still moving beneath their feet. If stories like this, the ones where old data quietly rewrites what we thought we already understood about a place we assumed was finished changing, are what you come here for, stay close, because there is more still shifting just beneath the surface.